let's kick things off. The sheer ambition of what we're diving into today, it's pretty astounding.
It really is.
Imagine trying to find like a hidden connection, a code linking the quantum world, which is already weird enough, to our own experience, consciousness.
Mm-hmm.
And that's exactly what this research is attempting, using something they call fixed points as the key.
Right.
So for you, the learner, always looking for that deep knowledge, but, wanting it efficiently, this is your shortcut, a deep dive into some real cutting-edge science.
It's definitely frontier stuff.
The big idea here is that these snable points, these fixed points, they aren't just abstract math. They might be fundamental in both quantum systems and how our own minds work.
It's a quest with breathtaking scope, really, trying to bridge that gap, the tiniest scales of reality and subjective experience. It shows how curious we are.
Totally.
And this research we're digging into proposes a unified mathematical way to do it, all centered on these invariant states, these fixed points popping up in both places.
Exactly. So our goal for this deep dive is to get a handle on these fixed points. How do they show up in things like superconductivity?
Yeah.
And incredibly, maybe even inside our own heads, in our thoughts, the hope, this could be the link, the connection between physical quantum stuff and our inner life.
It's like finding a stable pattern in chaos.
Yeah, like a melody that stays the same even when the music around it changes. That stable bit, that's our fixed point.
And what's really interesting is the theoretical groundwork they're laying. They're merging ideas that usually live in completely separate boxes.
Right.
Quantum physics concepts, invariance, stability, symmetry,
right.
The rules of the quantum world. And mixing those with ideas from philosophy of mind about consciousness being, fundamental, not just reducible to brain activity.
Okay, so at the core is this term, multidimensional scalar complex fixed points. Sounds like a mouthful.
It does, but let's break it down.
Please.
It's basically a state that doesn't change.
Yeah.
That stable thing we mentioned. But it exists in a really complex information space.
So not just one value, but like a combination.
Exactly. A stable recipe in a huge cookbook of possibilities. They talk about it as where algebra meets geometry, and they use a neat analogy, the hypotenuse of a right triangle.
Ah, Pythagoras. Okay, how does that connect?
Well, the hypotenuse length is fixed by the other two sides, right? It's a geometric invariant, a fixed ratio as long as it's a right angle.
Right, okay.
So similarly, these multi-dimensional fixed points in quantum systems are like fundamental unchanging anchor states. The system's behavior kind of locks onto them.
And here's where it gets really wild, connecting this to our brains.
Mm-hmm.
The research suggests the super detailed way our brains are wired and process information that can also be modeled using these fixed points.
Yes, they bring in David Chalmers' idea of an isomorphism.
Isomorphism, like a mapping.
Pretty much. A structural similarity, like how a map structure mirrors the actual roads.
Mm.
Here, it's suggesting a mirroring between the brain's processing and the structure of conscious experience itself.
Wow.
And they lean on two key principles from consciousness studies to back this up. First, the principle of structural coherence.
Structural coherence? What's that?
It suggests the structure of your experience, seeing the world in 3D, directly reflects the structure of the neural processing going on. The physical pattern matches the subjective pattern.
So invariant features in the brain activity should show up as invariant features in my experience.
That's the idea. And the second principle is organizational invariance.
This one sounds really out there.
It kind of is.
Yeah.
It's as if you have two systems, could be brains, could be silicon chips, with the exact same fine-grained functional organization. They should have identical experiences. The physical stuff doesn't matter as much as the causal pattern, the way information flows and causes things to happen.
Yeah.
That pattern is the fixed point.
Like the plot of a play is the same whether actors or robots perform it if they follow the same script.
Exactly, that kind of idea. And these two principles lead them to what they call a double aspect viewpoint.
Double aspect, meaning
information itself isn't just physical or mental. It have two sides. A physical side, how it's processed, and a phenomenal side, what it's like to be that processing.
So mind and matter aren't totally separate.
That's the implication. These fixed points are where the physical side and the phenomenal side kind of lock together. They both arise from some deeper invariant structure in information itself.
So information is the bridge. They mentioned Shannon's theory.
Yeah, defining information as basically differences that make a difference. Here, they're saying it has this dual nature, physical, like quantum states or brain signals, and phenomenal our subjective experience.
And the argument is when the physical side hits a stable fixed point,
The experience associated with it also becomes stable and reproducible. A stable physical pattern means a stable subjective quality.
okay, that's the theory. Where do we actually see these fixed points in the quantum world?
Well, quantum relativistic dynamics is full of examples. Yeah. These fixed points are crucial for understanding things like phase transitions, these things called topological invariance, and just the general stability of systems.
Okay, let's start with phase transitions, like water freezing, or they mention superconductivity. How do fixed points play in?
Right, superconductivity is a great example. When a material becomes superconducting, it's essentially settling into a fixed point.
How so?
At a critical temperature, electrons pair up and condense into this single unified quantum state, a coherent state. And that state, the London theory, helps explain its stability. It's incredibly robust against small disturbances. It's a fixed point defining the whole new behavior of the material.
Wow, okay. A totally new, stable behavior just emerges, and then topological insulators, they sound even weirder.
They are fascinating. They have this built-in protection for certain electronic states, thanks to what are called non-trivial topological invariants.
Topological invariance, what does that mean, practically?
It means the fundamental symmetries of the system could be simple, could be complex topological ones, basically enforce a fixed point, like an unchangeable characteristic or label in the space of possible quantum states.
So it's resilient.
Incredibly resilient. It resists disturbances. And mathematicians have ways to characterize these, like using Chern numbers. Think of them as unique ID tags for these protected states.
So the system has this inherent stability, this fixed point protecting it. And it's not just single values, right? They talk about multidimensional fixed points.
Exactly. The invariance isn't just one number. It's like a complex, synchronized dance. The fixed point is the whole coordinated pattern.
Okay.
In quantum fields, different components, how the system behaves under rotation, phase changes, its quantum numbers, they all combine. And this complexity, this multidimensional stability, starts to sound a bit like the complexity of our own mental states, doesn't it?
It does, yeah, that complex feeling of perception or thought. They even have that figure 1 diagram showing the steps.
Right. It shows it's a process. Pairing a state, finding symmetries, hitting critical parameters, a phase transition happens, and boom, you get this stable, multidimensional fixed point leading to real-world observable properties.
Okay, so that's the quantum side. Now let's pivot. How does this fixed point idea apply to us, to cognitive systems?
Good question. If quantum systems find stability through symmetry, how do our incredibly messy brains generate stable experiences?
Yeah, how do we get stable consciousness from all that neural firing? This leads to neurodynamics and functional invariance. What's a functional invariant in the brain?
Think about your ability to say, tell me what you're seeing right now. That ability, accessing the information, forming words, it's a functional capability that stays pretty consistent, even though the exact neurons firing are changing constantly.
Ah, okay. The function is invariant.
Exactly. And that principle of organizational invariance comes back here. If something else, maybe AI, had the same functional setup for reporting, it should theoretically have a similar kind of reporting capability, or maybe even experience.
The structure matters more than the substance. Okay. They also mention complex scalar fields for brain function, like extending the quantum idea metaphorically.
Precisely. It's an abstraction. The field represents all the dynamic stuff in the brain, oscillation frequencies, amplitudes, phases, and a fixed point in this field could represent something like cognitive readiness, or maybe even awareness itself.
Interesting. They mention the 40 hertz oscillations Crick and Koch talked about.
Yeah, as a potential invariant pattern linked to consciousness, a stable rhythm that might help bind information together across the brain.
And they bring back the hypotenuse analogy again. How does that fit with the brain?
It's a metaphor for anchoring. Just like the hypotenuse ratio is fixed in a right triangle, maybe an invariant structure in neural processing anchors our conscious experience. It provides stability despite all the noise and fluctuation.
Which ties back to that structural coherence idea. Stable experience mirrors stable processing.
Exactly. The subjective stability reflects an underlying physical stability.
And Table 1 neatly compares the quantum and cognitive fixed points, how they're similar, how they differ in terms of invariance, parameters, robustness. It's a useful comparison.
Mm-hmm. And the connections get even richer when we look at light-matter interactions. The research points out these are also governed by topology and show fixed-point behavior.
Okay, so light interacting with matter, and fixed points show up there too, often linked to quantization. What does that mean here?
Quantization here means things can only exist in discrete, specific states or levels. A classic example is the quantum Hall effect.
Quantum Hall effect. What happens there?
You can find electrons in 2D and apply a strong magnetic field. Their movement, their energy levels become quantized. They can only take on specific, discrete values. And these values, like electrical conductance, act as fixed points.
And they're stable.
Remarkably stable. The underlying topology, the sort of geometric structure of the electron paths, is conserved even if you tweak the magnetic field a bit. It's a powerful parallel to how our experiences can feel stable despite sensory changes.
Like a fundamental structure dictating the allowed states. And topological field theories help describe this mathematically.
Exactly. They provide the math to define these fixed points rigorously. They let physicists identify invariants like those Chern numbers again, which act like fingerprints for the system's state.
So metaphorically, for the brain, these invariants could be like persistent patterns of connection that enable consciousness?
That's the analogy they're drawing. It's this interplay of geometry, the structure, and the information being processed. The hypotenuse comes back as that geometric metaphor for stability.
Right, information structured to keep its integrity.
And this is where the double aspect theory is key again. The idea that every physical information state also has a phenomenal side, what it's like. This bridges the quantum invariance in light matter physics with the subjective stability we feel.
Figure 2 shows that interaction visually photon in, electron responds, topology ensures invariance, leading to quantized states, the quantum fixed point.
Which brings us right to the deep end. Observer consciousness, and why we might need non-reductive views.
Meaning consciousness isn't just brain activity, but maybe something more fundamental. This is the hard problem, right?
Yes. Chalmers' famous hard problem.
Yeah.
Explaining functions, how we report things, tell things apart, doesn't seem to explain the why. Why is there subjective experience, the what it's like feeling at all?
So how do fixed points help with that?
The researchers suggest that these invariant features in our cognitive processing, the stable patterns we've discussed, aren't just physical. They propose these fixed points exist in the realm of subjective experience itself, reflecting that structural coherence and organizational invariance.
Okay, and this connects to naturalistic dualism and the double aspect theory. How do those fit in?
Well, naturalistic dualism treats consciousness as a fundamental part of nature, like mass or charge, not reducible. Chalmers argued we might need new fundamental principles to explain it.
Right.
The double aspect theory offers a way forward by saying information is that bridge. It has both physical and phenomenal aspects inherently. So those fixed points in information processing, they include an experiential component by their very nature.
So when the brain hits a stable information processing state, a fixed point, there's a corresponding stable experience built in, not just a functional outcome.
That's the proposal. And they mention neural correlates, like those synchronized oscillations, as evidence for stable brain states linked to consciousness. Organizational invariance reinforces that the pattern is key, not the substrate.
Silicon or neurons, same pattern, same experience.
In principle, yes. So observer consciousness emerges at these stable, fixed points where the information structure is robust, where the physical and phenomenal aspects converge and stabilize.
And figure 3 lays out that flow. Sensory input, processing, binding, invariant dynamics emerge, information becomes available, and then stable subjective experience arises. A whole chain leading to that conscious fixed point.
Now, given how complex this all is, the research makes a crucial point.
Yeah.
We need computational tools to actually explore these ideas.
Right, you can't just intuit this stuff. They mentioned Monte Carlo simulations and density functional theory, DFT, for the quantum side.
Yes. Monte Carlo methods are great for modeling systems with randomness, like quantum mechanics, helping see how stable states or phase transitions emerge from fluctuating behavior. DFT is a workhorse for calculating electron behavior in materials, helping pinpoint the parameters that create stability and invariance to the fixed points.
And for the cognitive side, neural network simulations and information processing models.
Absolutely essential. We use large-scale simulations to model brain dynamics. By building these models based on principles like structural coherence and organizational invariance, we can look for emergent stable patterns, potential fixed points, and see how they relate to simulated conscious-like states.
They even compare quantum modeling software like Quantum Espresso to neural simulation tools.
Yeah, showing the parallels in approach. But the really novel idea is integrating physical and cognitive simulations.
Combining them. How would that work?
By building hybrid models. Imagine using Monte Carlo methods within a neural network simulation, or mapping parameters between DFT results and brain models. This could let us directly compare how fixed points arise in both domains.
And potentially test that double aspect idea, mapping a quantum fixed point to a neural one.
That's the hope, gaining real insights into how physical invariance might relate to phenomenal stability. Table 2 gives a good overview of all these methods, their domains, outputs, and relevance to fixed points. It really highlights the interdisciplinary nature.
Okay, so all these threads, quantum physics, consciousness studies, computation, they all come together in the final synthesis, this unified framework.
Exactly, pulling it all together.
So what are the absolute core pillars of this framework?
There are basically 4. First, invariant information structure, the idea that stable information patterns, fixed points, underlie both quantum and cognitive systems. Second, the dual aspects of information having both physical and phenomenal sides.
Okay, 2 more.
Third, structural coherence and organizational invariance. These principles ensure the robustness of the fixed points and link them to the system's causal structure. And fourth, the need for computational validation, using simulations to confirm and study these fixed points.
And how does the framework weave these into one big picture?
It views fixed points as stable attractor states in a very complex, multidimensional space that includes both physical and cognitive factors.
Attractor states, like states the system naturally settles into.
Precisely. So quantum phase transitions leading to stable states like superconductors, or the stability from topological invariance, that's the system finding a physical fixed point.
And in the brain.
Neurocoherence, the synchronized activity linked to consciousness, emerges from stable, invariant, dynamical patterns, cognitive fixed points. The key is representing these with those scalar, complex fields, capturing both quantity and quality. And crucially, the invariance holds regardless of whether it's particles or neurons.
This seems like it has huge implications.
Yeah.
And points towards future work.
Absolutely. First, it could genuinely bridge disciplines, creating a shared language for quantum physics and cognitive science. Huge potential for collaboration.
Yep.
Second, it offers a new angle on understanding consciousness, maybe helping tackle the hard problem by focusing on these invariant structures.
No.
Potential technological innovations. Maybe neuromorphic computers designed around these stability principles.
Inspired by biology, but based on these fundamental invariants.
Could be. And future research is wide open. Refining the math, designing experiments to actually observe these states, better integrating computation and brain measurements.
Figure 4 wraps it all up visually. Quantum dynamics, leading to fixed points, the dual aspect infrastructure connecting to neural dynamics and cognitive invariance, then conscious experience emerging as stable observer states, all feeding into the unified framework.
So just to bring it home, the key takeaways we've covered. This research proposes that invariant information structures, these fixed points, are fundamental to both the quantum realm and our conscious minds.
Right. And that information itself might have these 2 sides, physical and phenomenal, linking matter and mind through these stable states.
And principles like structural coherence and organizational invariance explain why these fixed points are stable and reflect the system's underlying organization, no matter what it's made of.
Plus, the absolute necessity of computational tools to actually model, test, and validate these complex ideas.
Exactly. It all points towards this unified framework as a potentially powerful new way to think about reality, consciousness, and the connections between them, maybe even inspiring new technologies down the line.
So as you, the learner, mull this over, here's a final thought. Could the stability we see in the quantum world, the way systems settle into these fixed points, be fundamentally, intrinsically linked to the stability of our own conscious awareness? Is the universe itself maybe constantly seeking out these stable invariant states at every level? Definitely something profound to consider. Thanks for taking this deep dive with us.